Okay, so this is part A of Get to Know Your Data Packet 2022 edition. And so I'm going to be walking you through the data booklet, the first half of the data booklet, all the way to bond enthalpy, which I think is table 11. And we're going to be talking about every single calculation, things that you can cross out, things that you should really emphasize, and things like that, things that you need to know and you don't need to know. Now, for simplicity's sake, whether you're SL or HL, it is important to differentiate between that. So if you are SL, all your stuff will be in red and orange and maybe pink. Okay. So if you look at the data booklet later on, because I'm going to upload this to YouTube to Notability like I use Dropbox like I usually do, all the stuff written in red, orange, and pink, that's classified as SL material. When you look at the bluish side of the spectrum, as in blue, and then actually that's kind of just darker blue, and green, and we'll say kind of violet here, but it's a little bit hard to see that. So I probably will try to stay away from violet if possible. But the bluish side of the spectrum will be all HL. So there will be a differentiation in this data booklet when you look at it about what level's which. And so there are parts, today actually is fairly full of SL material. Day 2, which I recorded on Tuesday, there are big gaps. And so like there's a little bit of SL at the beginning of the class and there's a little bit of SL at the end of the lecture, but that lecture is only about an hour and a half long, so it's actually not too bad because there's a couple things in data booklet that we haven't talked about yet, which we're gonna talk about in class, and so I didn't want to review it on there yet because we haven't talked about it. But so also key thing, if you're printing it off my Schoology website, then you have the right edition. But make sure if you start Googling online and trying to find the chemistry data booklet, that it says 4th edition on it, because there were variations of this, kind of rough drafts of it, 1st and 2nd edition. There were some typos in there, and they were caught and they were corrected. And so the 4th edition is the final version that you're going to get on the IB exam. So you should get familiar with that. It's 44 pages long, front and back. It'll be printed kind of like the way y'all printed it yourselves. Okay. So, table of contents. Okay. Good thing is that the IB lists information that you need to know based on the order and topics that are arranged by the IB. And so the first few things, electromagnetic spectrum, fundamental particles, names of elements, that's topic 2 and 3. Ionization energy, that's topic 3. Then bond length and bond enthalpy and thermodynamics, that's topic 5. Oxidation states, there's a little bit of topic 3 in there too, but a little bit more higher level stuff. And so lattice enthalpy is topic 5, and then acid base is topic 8. So it does go in order, and there's a lot of this data booklet that you don't need to know for this year because the IB has removed some of the curriculum for y'all due to the pandemic. And so there's a lot of pages in here that you will not need to know. Yes. That's a good question. The multiple choice will progress in order, Tifa. So when you look at the 30 or 40 questions, depending on your SL and HL, the first few questions should be topic 1 and 2, and it'll progress. And the last few questions should be topic 10 or 20, organic chemistry. And then maybe like one extra like lab question at the end of that. But in multiple choice, it does go through the topics in order. So if you see a question like number 3 and you think it's a reduction oxidation reaction question, it's not. It's a different type because they do the multiple choice in order of topic. The short answer, I think they try to do that, but there's so much overlap in the topics and the questions. The main idea of the topic might be the in order of the question, but there may be other topics that are infused in there. So like number 1 is usually a calculation question. So like whatever topic that might be a empirical formula question. It might be a stoichiometry limiting reactant question. It might be a calorimetry question. It might be an acid-base question, neutralization reaction. But that's going to be usually the first question you see as a big calculation question. Now, after that, they'll probably sprinkle in like shapes and stuff like that and bonding, which is topic 4. And then they'll probably do a little bit of thermodynamics and then maybe some organic and stuff like that. But I wouldn't say it's as clear cut in the short answer that goes in order like it does in multiple choice. Multiple choice, it is always 2 or 3 questions each topic, we move on. So there's no doubt about that. That's a good question. Okay. So Relevant equations. The IB is really good about giving you some information so they can help you, but not enough information that will allow you to figure things out on the fly in the data booklet. So they're very, very smart about going, okay, if a student knows how to use the ideal gas law equation, but they just don't remember the equation, here we're providing it to them so that way that part of the memorization isn't the hindrance to them answering the question. And so all these equations are kind of the fundamental ones, but you still need to know how to use them. And there's some little kind of details that if a student doesn't know what they're doing and they just try to grab this equation out and try to use it, they're going to run into problems. And that's the intention of the IB, because it's not supposed to be that you can walk in without knowing anything and just use these equations to get answers. You have to have been familiarized with these equations to be able to do the problems they ask. Okay. So also, before I start this, the topic for each equation is listed on the left. Okay. So you can see that topic 1 through 10 is standard level, and topic 12 through 21 are higher level. So SL only has 4 equations that they need to know on here, these first 4. HL needs to know the next section, the 12.1 to 19.1, which we'll talk about as well. And so make sure you're kind of familiar with that. So with SL, you can stop looking at the data booklet right there. So there's only 4 equations that SL needs to know. Okay. So, and those topics are in order as well. Know that topic 1.3 equation is the first thing you'll see, ideal gas law. Okay, so let's talk about these equations individually. This first equation is the ideal gas law. Okay, PV equals nRT. I don't really like this as lowercase p. I prefer this as capital P, but it's their choice here. PV equals nRT. Now, things we need to know about each of those variables, okay? P is pressure. V is volume of the gas. N is moles. R is the gas constant. And T is temperature, okay? And the units do matter. You're going to find out that in a lot of IB chemistry, the units are what will make sure that you get the right answer overall. So they don't tell you the units for PV equals RT. That's the part they expect you to know when you're applying this equation. So they're giving you just enough to help you, but not enough where you can just figure things out on your own. So pressure is in kilopascals or pascals. Both are units of pressure measurements. Volume can be measured in decimeters cubed or meters cubed. Okay. Moles is just moles. The gas constant is joules per mole per Kelvin. And temperature is always in Kelvin. Now, the thing with pressure and volume is that the units have to be compatible with each other. And what that means is that if you're going to use kilopascals, you have to use decimeters cubed. And if you're going to use pascals, you have to use meters cubed. So they are paired up with each other so that you get the right ratio of pressure and volume in your equation. So keep in mind that you have to use kilopascals with decimeters cubed, and you have to use pascals with meters cubed. And they do give you the conversion between decimeters cubed and meters cubed later on, which we'll see. So again, not enough to be able to solve a problem with just that equation, but enough for someone that knows a bit about chemistry to figure out based on the equation that's given to you here. You also want to know is one of the things they like to do with gases is they'll incorporate the ideal gas law into the molar mass of a gas. Okay, because the molar mass of a gas is equal to mass over moles. And you can use PV equals nRT to solve for the moles, and the problem will give you the mass so you can find out the molar mass of the gas. This is usually kind of an empirical formula, molecular formula problem where they're incorporating different calculations into the same problem. So you'd be given the mass of the gas in the problem, you'd use PV equals nRT to solve for the moles of gas that mass occupies, and then you can divide them to figure out what the molar mass of the gas is, which then lets you figure out the molecular formula. Don't forget Kelvin is degrees Celsius plus 273. So keep in mind that conversion as well. Whenever you're dealing with temperature in chemistry, it should always be in Kelvin. The only time it doesn't matter is if you're taking the difference in temperature. Then it doesn't matter if it's in Kelvin or Celsius, but you should always default to having everything in Kelvin in chemistry. I can't think of a time where Celsius is acceptable on its own. So everything needs to be in Kelvin. Questions on that so far? Let me box that out over here. This second equation is from topic 2.2, and that has to do with wavelength and frequency of light. So wavelength is written by this symbol lambda, and frequency is written by the Greek letter nu. Okay, so what this says is the speed of light, which is c, which is 3.0 times 10 to the 8th meters per second, is equal to frequency times wavelength. And the units do matter. Frequency is in seconds to the -1 and wavelength is in meters because it has to match the units of the speed of light. So again, units really, really matter. We'll have a whole Saturday session about units and when they matter. Like it's actually already on YouTube, but I'm going to record it again. And so for SL, you need to know the relationship between frequency and wavelength. When frequency goes up, wavelength goes down. Okay, so they're inversely related because they're on the same side of the equation. So you want to know that inverse relationship. So like the longer the wavelength, the shorter the frequency. The shorter the wavelength, the higher the frequency. So understanding that relationship is an aspect of light that you need to understand, and being able to calculate that and make sure the units are correct is a really important part of this process. Huh? 8th. Yeah. That is also given in the values later on, which I'll show you. So you don't need to memorize that. Okay. I'm gonna write over some things right now. Q equals MC delta T. This is calorimetry. One of the biggest ways that especially SL students can use to calculate the enthalpy of a reaction. And so again, knowing what Q, MC, and delta T stand for and not making a mistake about assigning values is the big challenge for this. Q is heat of experiment. So the experiment you're actually doing in joules. M is the mass of water. Okay, most of these equations that we're doing is a reaction that is in a solution. So water is what's absorbing or losing heat. So you really want to emphasize that this is mass of water. And the thing is, the IB won't give it to you in grams because they want to know if you actually know what the correct value is. And so you have to know that 1 centimeter cubed of solution is equal to 1 gram of solution. Because what they'll do is they'll give you the grams of the reactant and then a volume of water. And if a student doesn't know what they're doing, they're just so trained to say, okay, I need a mass. I'm just going to find anything that has grams in this problem and I'm going to use that number. That's where they get it wrong, because it's not the grams of the reactant you care about. It is the volume of solution, which is their mass of solution that you use for here, because you're using the specific heat capacity of water, which is 4.18 joules per gram degrees Celsius. So everything revolves around water here. And that's why the mass is really important, because again, students that don't know what they're doing will just assume, okay, this is the only grams of my problem. That must be the grams I use here, but it's not. Because you have to know that 1 centimeter cubed of water is equal to 1 gram of water. So if I have 500 centimeters cubed of water or solution, that means I have 500 grams for my Q equals MC delta T, not 4 grams of NaOH or things like that. So really important. That's the big thing that you star. Yes, Tifa. Correct. Yeah, that's a good question, but that has to line up with the C units, right? The specific heat capacity units are joules per gram degrees Celsius. Okay. Delta, yeah, I'm about to say that. So delta T is the change in temperature. So TF, the final temperature, minus the initial temperature. And it will be the same in Celsius or Kelvin. The difference in a degree in a Celsius and Kelvin are the same. So whether you have it in Kelvin, you subtract, or whether you have it in Celsius, subtract, it should be the same value. Now, don't subtract and then add 273 to what you subtracted, because then you're converting your difference, and that doesn't make any sense. So either have it in Celsius and subtract, or turn it into Kelvin and subtract, but don't subtract and then convert it to Kelvin. No, it doesn't, because it's a difference, right? So adding 273 to your difference throws everything off. But you're right. Like if you're just doing temperature, yeah, you should add 273 always. But I just had students go, oh, like it's 25 minus 22, so it's 3 degrees Celsius, so it must be time plus 273, so it's 276 Kelvin difference temperature. No, it's just 3 degrees, because it doesn't matter what unit you have it in. Yes, you are, and we'll see that in a little bit. That's a good question. Now, here's the thing to keep in mind. If your delta T of your water is negative, that means it's endothermic. Because remember, whenever you measure temperature, it's always of the surroundings, never, ever, ever of the system. So if you see a temperature of a system of your water go down, your thermometer goes down, that's because it's part of the surroundings. And if the temperature of the surroundings is going down, then that means the system is absorbing heat from the surroundings. If your temperature of the water is positive, that's exo, because if the temperature of your water is going up, that means your system's releasing heat into the water, and that's why the water is getting hotter. So it's it feels kind of weird, but you only measure the temperature of the surroundings. So whatever happens to the surroundings, that's the opposite of what happens to the system. Now, so that also means that Q of the water is equal to negative Q of the reaction. So you change the sign if you want the Q of the reaction. And then delta H of the reaction is equal to Q of the reaction divided by moles of reactant. I'm sorry? Delta H of the reaction is equal to Q of the reaction divided by the moles of reactant. This is where the grams of NaOH that is in your problem comes into play, because you need to figure out how many moles of NaOH was actually giving off that amount of heat, and that's where that value goes. So you don't use the grams of like NaOH in the problem for Q equals MC delta T. Use it for moles of reactant right here. Question, Sammy? Oh, yeah, Tony. Yes, Sammy. Yes, but it'll usually be given in the form of grams or maybe like a molarity and a volume. So you have to convert it to moles, right? So this is one of those complex problems where you see they're not giving you enough information to solve the whole problem with this data booklet, but they're giving you enough so that you can go toward the steps of doing it. So yeah, it's tricky because you'll get a grams in there and a lot of students will think that's the mass, but it's not. It's actually used to convert to moles in the delta H calculation. And that's something we'll kind of look at when we practice problems and things like that. Not today, though. Yes. So we do not do. So yes, C4 is irrelevant here, Tifa, for us. And I'll show you what you can cross out in a little bit when we get to that point. Okay. This last equation for SL is calculation of pH. Okay. Now, these are the same. So H3O plus and H plus are synonymous to each other. You don't need to, like, they're the same. There's no difference between those two. It's just how it's written in the equation, but there's no difference between them. What you need to remember is that lowercase p always means negative log. Okay? Because it could be pH, it could be POH, it could be pKa or pKb for a higher level, but p always lowercase p always means negative log. Okay? And so POH is equal to negative log of OH minus. And you also have to be able to reverse this as well. If I give you the pH, you have to know by reversing this equation here that my H3O plus concentration is equal to 10 to the negative pH. So I bring the negative over and then I 10 to the power both sides to get rid of the log, and that's what I end up with. H3O plus equals 10 to the negative pH. Or OH minus is equal to 10 to the negative POH. They're both acceptable. And for SL, you want to know that pH plus POH equals 14. Because for SL, you're only doing it at standard temperature and pressure, so that is always true. For a higher level, this is pKw, not 14 always. So you have to be careful about that. If it's not at 25 degrees Celsius, then 14 is not 14. It could be 13, or it could be 15, or it could be 13 and a half. But yeah, if you're higher level, I mean, you can write it just as pKw. Yeah. Right. I don't know why they choose to use that lowercase p there. Maybe they're just trying to, because pressure I've always written as capital P. But no, I don't think there should be anywhere else that's a lowercase p other than that. Yeah, pH and POH and pKa, pKb and stuff like that. That should be the only time. Okay. Questions about all of that stuff for SL? Okay. It's only 5 equations, but it's a lot to know for 5 different equations. Because again, SL math is limited in what you can do. It's stoichiometry, it's empirical formula, it's ideal gas law, it's calorimetry, it's Hess's law, and it's pH calculations, really. I mean, there aren't that many other calculations you have to do. Maybe combustion empirical formula as well, but like, so it's pretty easy to kind of expect one of those calculation problems to be on your test no matter what. With SL, it's kind of, I mean, with HL, it's a little more hit and miss because there's so much more material. You may miss a lot of calculations that you don't need to do. Okay. So HL. HL, you have really only 5 equations as well. It's just 3 of them are written in different formats, but they're the same equation. So the first one is E equals H nu, which is used to calculate the energy of a photon. Okay, so the energy of a photon is energy in joules. H is Planck's constant, which is 6.63 times 10 to the negative 34th joules times seconds. And then nu is our same old frequency, which is in seconds to the negative 1. So again, the units work because Planck's constant is joules times seconds. You multiply by 1 over seconds, you end up with joules. So the units are all, again, about matching up so that you end up getting the correct units in your equation. Okay. Now, the only thing I would warn you here is that, let's say you're given bond enthalpy. Bond enthalpy is in kilojoules per mole of photons, okay? So if you're going to use bond enthalpy, you need to, convert it to joules and then divide it by 6.02 times 10 to the 23rd because you only want 1 photon. So keep in mind that if you're given bond enthalpy, that it's in per mole. And so if you want to do it per photon, you have to divide that number by 6.02 times 10 to the 23rd. It's going to be a very, very small number. That's the point. So remember that you have to get the energy of 1 photon, you have to convert bond enthalpy to joules per photon. So be really careful about that. That's kind of one of those places that students trip up. So if it's per mole, you would divide that value by 6.02 times 23rd. So let me show you kind of this way with factor label. So if you think of a number like this, well, 1 kilojoule is 1,000 joules, right? And 1 mole is 6.02 times 10 to the 23rd. So now all your units cancel out, and you're left with joules per photon. So that's one way to do it. Okay. Oh, sorry, is there chat? Oh, I haven't done it yet, Grant. Also recording. Okay. All right. Continuing on with higher level. This equation here, okay, this is for spontaneity and Gibbs free energy. So remember, for a reaction to be spontaneous, your Gibbs free energy has to be less than or equal to 0. And it is dependent on your enthalpy and your entropy and the temperature. Okay. So how is this equation? So what does this equation not tell you that you need to know for these calculations? What it doesn't tell you is the units, because delta H is usually in kilojoules and temperature is in Kelvin, but delta S is usually in joules per Kelvin. So your kilojoules don't match up with these joules, and so you have to do a conversion before you can add or subtract them to each other. That's what they don't tell you in this equation, and that's why a student that just uses this equation that doesn't remember it gets it wrong, because they forget about units. And they just plug their delta H and delta S in here without writing units out, and they don't realize that one is in joules and one's in kilojoules, so you can't just subtract them. You have to convert one of them to kilojoules or convert them to joules to get the final answer. That's the big thing. The second thing of this is also using this equation to know qualitatively when it's spontaneous, right? So like, because remember, delta H and T delta S, delta H can be positive or negative. S can be negative. Oops, sorry, I didn't write in the right order. Like this. So there's 4 possible scenarios of whether it's going to be spontaneous or not. And so if it's positive and negative, then that's a positive minus a negative, which is a positive, so this is never spontaneous. If it's a negative minus a positive, that's always spontaneous. Now it's a negative and a negative, then you want low temperature here because you want T delta S to be as small as possible because it's hurting you. Over here, you want high temperature because in the second row, entropy is actually helping you, so you want that term to be as big as possible so you get a negative number. But there's not a specific value for temperature that's considered high or low. It's relative to the reaction itself. So you do want to think about that when you're looking at this equation. And again, I don't want you to memorize that table. You can figure it out on the fly in the test. Don't bother memorizing 8 pieces of information when you can just plug those signs in on your own and figure out on the test. You're better off that way, to be honest with you. You got enough stuff to memorize. This table like this is kind of is a waste of memory. Yes, Tifa. Well, it's negative T times delta S. So like, I guess if you want to think about it, I'm kind of putting negative as delta S. That's entropy. Yeah, that's the entropy of the equation. That's their S value. The measurement of disorder. Enthalpy. Enthalpy. Yes. Yeah. It depends on what you do, but usually it's in kilojoules. So usually you want to convert your delta S to kilojoules and then subtract. Depending on what the question asks you for, yes. If they just ask you to solve Gibbs free energy, you could write in joules or kilojoules and it'd be okay. But read the question carefully because usually they include the unit they expect the answer to be in the question. So usually what they'll say is, what is the delta G, comma, in kilojoules, comma, which tells you that I have to have my answer kilojoules because they won't accept it in joules. So be careful about that. Okay. Now, these 3 equations here, I don't know why they give you all 3 equations. It's the same equation, just written in different forms. I think that you should focus on this form of the equation here. This is used for activation energy. And I think y'all didn't get a chance to go over this last year. And so this will be something that we will also review or learn in class for a higher level. But we're using this to measure the activation energy of a reaction because this equation is very much so y equals mx plus b, where y is natural log of lowercase k, negative EA over R is m, 1 over t is x, plus natural log of a, which is your y-intercept. And so what they do is they usually give you a graph of this, and the slope of this line is equal to negative EA over R. And R is the gas law constant. It's still 8.31 joules per mole Kelvin. But we'll talk about that a little bit more. I want you to write it down, but it may not mean a lot to you right now, which is understandable. Oh, that's this equation, Marissa, broken out, so you can see how it matches y equals mx plus b format. So like, you know, like a linear equation is y equals mx plus b, right? Y in this case is natural log of k. M is negative EA over R. X is 1 over t. Yeah, sorry, that's, oh, yeah, it's hard to, oh, sorry. There you go. It was kind of matched, crossing over the black lines, so it was hard to see. Does that make sense? Okay. Now, two last HL equations. This one, another spontaneity equation, but now it's related to equilibrium, where you're dealing with K, capital K. And so what you want to focus on here is, again, using the equation, but that for delta G to be less than or equal to 0, you want K to be greater than 1. That's the main idea with this equation. Okay. So this is related to equilibrium. And they also make you do it relative to cell potential in topic 19, because delta G is equal to negative NFE. Remember, N is number of electrons, F is 96,500 coulombs per mole, and E is your cell potential. So you want E to be greater than 0 so that your delta G is less than 1, or less than 0, excuse me. You want E to be positive, so that way when you plug in all the values, you get a negative delta G, because it's negative NFE, and N and F are always positive. So it's only E that determines whether the reaction is spontaneous or not. Remember, N is the number of electrons you cancel out when you balance half reactions and combine them together. So whatever the number of electrons are that you cross out, that's your N. Okay. Now, everyone can cross out this next section right here, A.5 to B.7 here, because that's optional material, which we don't have to know, because there's no option curriculum this year. And also you can cross out all of this on the next table as well. So you don't need to know any of that. So that is a little bit of a relief. It always feels good to cross stuff off a data booklet. Yes, Marissa. Oh, coulombs per mole of electrons. Capital C, moles to -1. Oh, it's just volts. Yes. Yeah, because that way when you take the natural log of it, you get a positive number. Yeah. No, because like this year and last year were exceptions to the rule, not like the normal. So they probably print out all these data booklets way in advance, and so they're just being consistent about that, because they don't want, because I think the problem is, like, if teachers are using this data booklet because that's what they've always had, and then when they get to the exam, it's cut parts out, that's also very confusing as well. So it's better to go, okay, you know what the standard data booklet is going to look like, just know that you don't need to know these parts of it. So yeah, they don't cut stuff out, and so it should be the exact same data booklet for your mock exams and your final exams that you're seeing right here. And that's why I think getting to know your data pack is really useful. Because once next year, if they go back to the normal curriculum, then they'll just use this again. That stuff will come into play. But you don't have to do every option. You only do one option. So no matter what option you do, like 3/4 of those equations aren't useful for you. Okay. Physical constants in unit conversion. So now these are the constants that are used in your equations for you to be able to do calculations. Okay. So Avogadro's number, SL material, stoichiometry. Okay. So calculating particles. Okay. So 1 mole is equal to 6.02 times 10 to the 23 units. So it doesn't matter what you're talking about. If you say 1 mole of something, that means you have 6.02 times 10 to the 23 of that something. So like with photons, if I have bond enthalpy, which is per mole, that means I have 6.02 times 10 to the 23 bonds that I'm measuring for. So if I want the energy of 1 photon, I have to divide that bond enthalpy by that to get the energy for 1 bond. Okay. gas law constant, okay? For SL, this is PV equals nRT. That's the only time I think you would need to use the gas law constant. For higher level, you have to use it in natural log of k is equal to lowercase k is equal to negative EA over RT plus natural log of A. But you also have to know in delta G is equal to negative RT ln of K. So there's some additional times where you would need to use the R value that is not SL. Molar volume of an ideal gas at STP, okay? Notice it is 22.7 decimeters cubed per mole. Be careful with what chemistry books that you use because the IB defines STP as 100 kPa and 273 Kelvin, which gets you 22.7. AP might do 22.4 because they do 101.3 kPa instead of 100. And so it is 22.7, and that's what you're expected to know, that 1 mole of gas at STP occupies 22.7 decimeters cubed of volume. So that's what you want to convert. Okay. Also useful, 1 decimeter cubed is equal to 1,000 centimeters cubed, or 1,000th of a meter cubed. So they give you that conversion in the data booklet as well, in case you forget the conversion between decimeters cubed and centimeters cubed. That's given to you in your data booklet. STP is for gas laws. So if we're doing PV equals nRT, or like even the smaller like combined gas law and stuff like that, it's those conditions. SATP is standard ambient temperature and pressure. So this is for thermo, your delta H, and like equilibrium and things like that. Because those are the realistic ones. Okay. So speed of light, that is used in topic 2 and 12. So this is where, well, actually it's only in this equation, C equals nu times lambda. So that's when you would use the speed of light for a calculation here. Okay. Specific heat capacity of water, that's your Q is equal to MC delta T. Usually you'll do it in 4.18 joules per gram degrees Kelvin, unless you have a really massive sample where it's more than 1 kilogram. I guess you could use 4.18 kilojoules per kilogram, but it's still the same value, right? Because the ratio is the same. A kilojoule to a kilogram is the same as a joule to a gram proportion-wise. Oh. So I usually just use 4.18 joules per gram degrees Kelvin or degrees Celsius, and just make sure my units match up with that. Planck's constant is higher level. That's your E equals h nu equation. So the energy of a photon. 6.63 times 10 negative 34 joules times seconds. Faraday's constant is your delta G is equal to negative NFE, and also electroplating. Because you have to know that 96,500 coulombs is equal to 1 mole of electrons. So that way you can figure out how many moles of metal you can plate from that. So you need to know for both of those. Ionic product constant of water, 1 times 10 negative 14 at 298 Kelvin, that's standard. So that's SL and HL. So KW is equal to 1.00 times 10 to the negative 14. For HL, there's a whole nother table later on that outlines the dissociation constant for water. Sorry? Yeah, that's just what that value stands for. You do not need to know the AMU to kilogram conversion, so that is not necessary for you. So one more thing we can cross off. Knowing it at 2298 is SL. For HL, you have to know it at other temperatures, which is a table that's later on in that booklet, which I don't think we went over on Tuesday, so I'll have to re-record this on Friday as well. Okay. Electromagnetic spectrum. Understanding the different types of electromagnetic radiation there are and how their energy is ranked. Okay. Now, I would focus on knowing kind of this major area here, knowing what visible light has the highest energy and has the shortest wavelength, which is violet, which one has the longest wavelength, which is red. And then IR, infrared, has a longer wavelength than red, and UV, ultraviolet, has a shorter wavelength than violet. I would know that if you're SL, like knowing that order of the wavelength and frequency. Remember, the longer the wavelength, the lower the frequency. Okay. So the longer the wavelength, the lower the frequency. For HL, you need to understand that energy is increasing this way. So the higher the energy, the higher the frequency, and the shorter the wavelength. Okay, so you need to know that relationship between those things. Correct. So radio waves have the lowest energy, the longest wavelength, and the lowest frequency. That's what allows radio waves to travel long distances and transmute music and like broadcasts, because they don't take a lot of energy and they can cover a long distance each wave. Whereas gamma waves and X-rays are really high powered energy, and the frequency is so high it can pass through your body. That's why X-rays actually work, because the frequency is so high it's able to oscillate in between your through your skin layer, so you can actually see into your body. But that's a lot of energy, and that's why you wear a lead vest around the internal organs, your vital organs, because you don't want that energy to hit your internal organs, because it might actually do damage to them. So you always wear like a lead vest to block out X-rays from hitting your organs and stuff like that. Yeah. Exactly. That's why whenever you, even like dental X-rays, you have to wear that vest on, because you want to protect your vital organs. Even though, to be honest with you, that dental X-ray machine is pretty targeted, but just precautionary thing. Yep, exactly. To block out, kind of protect your body from the rest of the X-rays. Yeah. No, it's not going to damage your arms in the same way as the vital organs do. You know, because like your skin cells and stuff like that repair and regenerate fairly easily, but your stomach and your heart and your lungs, those cells are much harder to repair, and so yeah, it wouldn't do the same kind of damage. Yeah, you're not supposed to do X-rays, exactly. Yeah. Okay, fundamental particles, I would cross that out. Okay. there's really no value for these values in calculations or anything like that. So I wouldn't worry about fundamental particles. Okay. The next 2 pages are names of elements, and that sounds really silly, but there's a lot of elements that students mix up because they're very similar in name and similar in symbol. You know, the default ones that I've always seen that students mess up are like sodium and sulfur, because sodium's Na, sulfur's S. Potassium and phosphorus, K versus P. You know, copper versus cobalt, copper Cu, cobalt Co. Magnesium and manganese, that's Mg versus Mn. I guess argon and arsenic, Ar versus As is another kind of common one. Not super common, but I'm just trying to think of ones that look very kind of similar to each other. Silver versus silicon. Because silver's Ag, silicon is Si. What else did I write on there? Oh. She just happened to. Well, Monday's video had a lot of technical difficulties, so it was kind of more difficult, and so.
Yeah, there was a fire drill and then all the power off.
Yeah.
And we had to stare, like the board went off, and we had to watch the.
On my laptop.
You had to watch. He set up his laptop here, and you couldn't see anything.
Yeah. So. A day of rest and clear my mind helped me think about a few more of them. But I think those are the main ones. Yeah, I can't think of anything else that's really kind of significant. But again, you have every single symbol, you have every single element on here, so there's no excuse for getting it wrong because you have a reference. Don't just assume you know it right. If you're unsure in any bit, use this table. Now, if there's an element the IB gives you that's not normal, like not common, they'll usually say something like, I don't know, they'll say tin Z equals 50, okay? What this is intended for you to know what the atomic number is. So any elements that aren't very commonly used, they'll tell you what the atomic number is so you can find it on the periodic table so you know what to hunt for it. So maybe tin is not a very common one, so they say Z equals 50. 50 is the atomic, is 50 the atomic number for tin? Okay, sorry, yeah.
Why is it put in alphabetical order?
That's a very good question. No, I agree. I kind of tend to agree with you, Marissa, that you should do an atomic number order, but I think Tifa's right. The rationale is if a student's trying to use the resource to find it and they're both in the same order, then it's not helping you, right? So, because if you knew the atomic number, you just go to the periodic table and read off the atomic number, but if you don't know it, then you're better off going by alphabetical order because that's the name that you're trying to find. So yeah. You're right, and like I think Tifa makes a good point too. Like I think that they're just trying to offer a different way for you to be able to find those elements, not the same number by atomic number. But I'm kind of with you, Marissa. Okay. So yeah, like Marissa said, these are all in alphabetical order in this section of the name, so that way you should be able to find it. So if you see silver, you should go to the S's and find silver, not go to the symbol of Ag. It should be in that order as well. Okay. Now, first of several periodic tables. There's like 4 periodic tables in this data booklet, and each of them have different information, and each of them are used for different problems. This is your standard one. The first periodic table is a standard one that you will do. This is the one that you get on the multiple choice section, because on the multiple choice, you don't get the whole data booklet, you only get the periodic table. So this is the one that you will get on the multiple choice. Yes? I believe so. Which is why I don't understand why they have the names split up on 2 pages now. Because now you have like 3 pages, but I think you do get the names. Yes. Yes. So you kind of do have to know it, but like I don't think the majority of the multiple choice questions are that. Like, and the stuff that they ask you about, like stuff that you need to know for data booklet, is kind of pretty obvious stuff. Like I've seen a time where they just literally ask you a multiple choice, what's the specific heat capacity of water? So that's something like that you've used a lot that hopefully you do know that's 4.18 by now, right? They're not going to ask you to recite an equation from the data booklet. So like what they might do is, because the data booklet gives you like all the ionization energies of all the elements, the first ionization energies, they might ask you about that in the multiple choice before you have that resource to answer the question, because you have to have a general understanding of trends. But it's not 40 questions of just memorizing stuff from the data booklet. But you still want to be familiar with the data booklet stuff. Yeah. Okay. This periodic table, okay? Notice that at every one thing also, notice at the top of every periodic table, the IB gives you a box example of what information is given you in there. So in this table, you're given the atomic number at the top, the relative atomic mass at the bottom, and the element symbol in the middle. Okay. Now, within this periodic table, you need to know a few things. One, you need to know some of the major elemental groups. There's like 4 or 5 that you really need to know. The first one, group 1, your alkali metals, your most reactive metals on the whole periodic table. Group 2, your alkaline earth metals. So alkaline metals group 1, alkaline earth metals group 2. Alkaline, correct. It's implied that they are bases, but they're not as basic as the group 1 metals when they react with water. So alkaline is like base-like. Okay. Now, over here, there's 2 major ones as well. There is the halogens, group 17, and then your noble gases, which are group 18. So I would know the names of those specific 4 groups on the periodic table. Yes, Marissa. No. They are the same reactivity, but they're the most reactive nonmetals. Yeah, so alkaline metals are the most reactive metals. Halogens are the most reactive nonmetals, but you don't really compare those two to each other. Yeah. Now, this is something I thought about while I was kind of doing this, but like electron configuration. Remember, the periodic table tells you a lot about electron configuration, because electron configuration is divided into sublevels. And the periodic table actually tells you where every sublevel is and everything you need to know about each sublevel, because S is found right here. The S sublevel is here. It's too wide because the S sublevel has 1 orbital and can hold 2 electrons. This section over here is your P sublevel, which can hold 6 electrons because it's 6 wide, and that means it has 3 orbitals. Okay, a lot of information to be gathered from these periodic tables. And thirdly, this middle section right here is your D sublevel, which is 10 wide, which is 5 orbitals. So if you forget how many orbitals are in a sublevel or how many electrons can be held in a sublevel, it's all posted for you on this data booklet if you know, on this periodic table if you know where to look. S is on the left, P is on the right, D is in the middle. Yes, Marissa.
The S supplement also includes.
Oh yeah, the HE. Yeah, technically it includes the HE as well, this one right here. Let me color this in a little bit more up here as well. So another little kind of trick to use on the from the data booklet. Now, one more thing on this before we move on. Relative atomic mass that's given to you on here is the weighted average of all isotopes relative to carbon-12. Okay. Now, so this is not one atom that's represented on the periodic table. It's an average of atoms. And so no one atom weighs 39.95 according to argon. Each argon weighs either 40 or 39, but that's an average. So most of them weigh close to 40. But no one atom weighs 39.95 because each isotope of an atom has a whole number because each proton, each neutron is 1 unit of mass. So you should never have a decimal mass number. It should be always a whole number. Okay. And when you calculate this, the way I find is the best way to do it is this. Do the percentage times mass plus percentage times mass as many times as you need to and divide it all by 100. I know some of y'all are good enough to convert percentages to decimals and then multiply and then add. Yes, you could do that, but I just have so many times where students make a mistake because they mess up the percentage conversion to decimal and then their whole answer's off. So I just say take that out of the equation, take that mistake out of the equation, just multiply the percentage the way it's written, times the mass, add them all up, and then divide your whole answer by 100, and you'll get the right answer every time. Okay. Because sometimes percentages that are decimals throw people off. They'll see like, oh, 0.05%. Well, that's already decimal, so I don't need to change it. No, it's actually 0.0005%. So if you don't think about it that way, then your answer can be off. And also, when you do this, your answer should make sense, okay? So if your isotopes are 28 and 30, then your relative atomic mass should be where? Between the two. So if you have 28 and 30 for your isotopes and you get 31 for your average, you made a mistake. Maybe you read a number wrong, maybe you wrote a percentage down wrong. But again, there have to be ways to check your answer to make sure they make sense. That's what I always emphasize when we go over calculations, like, does your answer make sense? If you have two isotopes, your average should be in between those isotopes somewhere. Now, is it closer to one another? That's fine. Depending on the weighted average, that's okay. But it has to be between those two values. So if you don't get a number between those two values, then you made a mistake and you need to go back and fix it. Everything has to make sense in chemistry. Okay. Questions on that? Let me see. Give me 1 second. 1, 2, 3. Okay, let's take a 5-10 minute break and then we'll continue on. So let's say 10 minutes. We'll say 1:25, take a bathroom break, get a sip of water, get a snack or something like that. We'll come back at 1:25 and we'll have probably about 30-40 minutes left of SL/HL material to cover, and we'll be definitely done way before 3. Okay, so take a little break right now, 10-minute break. Okay, so the next periodic table is melting points and boiling points of elements at 101.325 kilopascals. Okay, so what I want you to know about this is the point of this is to help you identify the state of matter at standard temperature. So the point of this is really to find out standard state of matter. Like, what state of matter is the element in at 25 degrees Celsius? Okay. And so each of these elements has a melting and boiling point. And the way I want you to think about it is this, okay? Because on the top, there's a melting point, and on the bottom, there's a boiling point. Huh? Yeah. And each of those numbers subdivides it into a different state of matter. So the way I would think about it is, if I think about a temperature kind of timeline, and this is negative 219.7, and this is negative 188.1, then anything lower than negative 219.7 is a solid. Anything between those two values is a liquid because it's melted but not boiled. And then anything above that is a gas. So when you think about 25 degrees Celsius, it's way above the boiling point. So it's going to be a gas at standard temperature. So all the elements, you can deduce the standard state of matter based on these values, melting points and boiling points. Okay. No, this is for you to determine what state of matter it is in at 25 degrees Celsius. So if I ask you what's the state of matter of fluorine at standard temperature, you would say, well, the boiling point is negative 188.1. So 25 degrees Celsius is higher than the boiling point, so therefore it must be a gas. Alexandra. Yeah, it's fluorine. Yes. So the numbers for the notches are different, but that's same idea. And also, I would say that this is also really useful because if you look at the non-metals, like the halogens here, you look at fluorine, chlorine, bromine, and iodine, and you look at the melting points or the boiling points. The boiling point for fluorine is negative 188.1, chlorine is negative 34.04, bromine is 58.78, iodine is 184.4. It's increasing as you go down the periodic table. And with nonmetals, like with covalent molecules, what must be increasing if the boiling point is also increasing? What reflects the boiling point of a substance? They're
IMFs?
IMFs, yes. They're IMFs. So what this implies is with a higher boiling point, you have stronger IMFs. And this would mean stronger LDFs due to mass. This is for all nonmetals, but it's best expressed in the halogens. You can see it the most clearly in halogens because you see some gases, some liquids, and some solids here too. So it shows you all the phases. Now, metallic bonding is very different, okay? And so if you look at metals, which I'm going to show you in a second, group 1 metals, you'll see the trend is a little bit different. Okay. If we look at these right here, okay, and we can look at the melting points of these metals like lithium, sodium, potassium, rubidium, cesium, and francium, the melting points, it's 180.5, 97.79, 63.38, 39.30, 28.44, and 27.00. It's decreasing as it's going down. That's because metallic bonding behaves differently than ionic and then covalent molecules. Metallic bonding is dependent on the size of the cation and the number of valence electrons lost, or the charge. Well, if you're all in group 1, the valence electrons lost is the same. They each lose 1. So what it matters is the size of the cation. And with metallic bonding, the larger the atom, the weaker the attraction to the delocalized electrons that form metallic bonding. So therefore, it's weaker attraction, which means a lower melting point. So you can see francium has the lowest melting point because it's the largest cation. And lithium has the highest melting point because it's the smallest cation. So its nucleus is closest to the delocalized electron, so it creates a stronger metallic bond. Sure. With metallic bonding, the size of the cation determines how close the valence electrons can be attracted to the nucleus, the positive charge. The larger the cation, the further away the valence electrons, the delocalized sea of electrons is to the cation, the weaker the attraction is. And so the larger, like francium is so large that the delocalized electrons are so far away, it's a very, very weak attraction. So it could melt almost at room temperature because the attractions are that weak. Now, this next table has to do with some trends. It has to do with some values that you may have to explain, okay? First ionization energy is standard level. I would say electron affinity is higher level, and electronegativity is standard level. We're going to break down each of these things and what they each mean now. Okay. And notice that they're kind of divided throughout, okay? First ionization energy, we'll write this up here in the blank space up here. First ionization energy is the first electron lost from a neutral atom. Okay. So the first electron that an atom loses makes it into a positive cation. So it's some gaseous species losing an electron, becoming positively charged, and producing an electron from its atom. So it's the energy it takes to remove an electron from a neutral atom in gaseous state. Everything's in gaseous state because that way you don't have some of the energy going into changing states of matter. It's all dedicated to ionizing that atom. So the general trend is as you go across, it increases because the increase in protons in your nucleus creates a greater attraction for those valence shells. Alexandra.
Well, next to the S plus, is that a G?
Yeah, it's a G. So generally speaking, as you go across, you have more protons, same energy levels. So that means that the atom has more of a stronger attraction for those valence electrons, so it takes more energy to remove. But there are a couple of exceptions, okay? Because based on how the electrons are distributed within an energy level. So I would say this. Every time you have an exception, okay? Every time you have an exception due to orbital diagram, okay? So if you're ever trying to explain an exception in a periodic trend, it's because of the orbital diagram, always. So if you're at a loss where it's like, okay, they want me to explain why nitrogen's ionization energy is higher than oxygen's, even though oxygen's further right, it has to do with the orbital diagram. So draw out the orbital diagram of each, and that'll help you see. Because like we said here, if you look at nitrogen and oxygen, nitrogen's 1402, oxygen's 1314. That doesn't make sense because oxygen should be higher according to our trend. So what it comes down to is this. Nitrogen is 2s2, 2p3. And oxygen is 2s2, 2p4. Okay. So in stability terms, which one has an easier time losing an electron? Oh, why, Sammy? Exactly. So oxygen has the incentive to lose an electron because therefore then I'll have 3 electrons equally distributed in the same sublevel. Nitrogen does not have that same incentive. In fact, losing an electron from its half-filled sublevel actually makes it more unstable, which is why it takes more energy. So anytime you're trying to explain a trend issue, draw orbital diagrams. That always explains the exception. Same way with boron and beryllium. Beryllium is 2s2, boron is 2s2, 2p1. So you would think because boron is further right, it would have a higher one, but it has a lower one because beryllium's 900, boron's 801. Okay. Looking at this orbital diagram, why does that make sense? Why is boron better at losing an electron? What's the incentive for boron to lose an electron as opposed to beryllium? It'll be more stable because it'll have lost the whole shell here. It'll lost the whole sublevel, so it doesn't need to hold on to that. Therefore, oops, sorry. Therefore, it's incentivized to do that and requires less energy to do that. So emptying a sublevel, emptying an energy level, resulting in a half-filled subshell, those are all incentives to lose an electron, which makes it easier to lose than normal. So exceptions are really big about that. I know what you're looking at me, Marina. I know that look. You didn't talk about this on Monday, Ms. Strong. I know. A lot of things going on in my head on Monday. This is why this is going to be the recording that I'm going to post.
It's so unfair, like, this is came on Monday. It's fine.
You'll see it again. This isn't the only time that you'll see it.
Yeah, like, it turns out, like, those guys are probably better.
I feel for the classes that have me first period on some days as well, because sometimes they get the first run through. They get the Mondays.
I like the first contact, like, it's a day.
Yeah. That one did get better over the day. Like the first one was okay, but like I felt like I got into the groove in the second and third one. That one was an exhausting one. No. Like
No, you don't practice much.
no, I don't have a script or anything like that. Like I think about the major points about it, but every class it will sound different. Like I don't even use the same verbiage and stuff like that. I just kind of speak based on kind of the flow of that class. So yeah, if you sat in all 4 classes, the overall idea is the same, but sometimes I use other examples. Sometimes I use better examples I think about throughout the day and stuff like that. But no, I don't rehearse it. No. No flashcards, no rehearsal. It's just very kind of extemporaneously. Extemporaneously. That means just like without like preparation, out of time, like without time. SAT word. Okay. I know, sorry. Yeah. Yeah, so that's 2 before. Okay. While SL's writing that, electron affinity for HL is gaining an electron to form a negative charge. And so this is where X in the gaseous state would gain an electron to form a negative ion. Okay. Yeah, just electron affinity. And that's first. Second would be then that same ion gaining another electron to form the 2- ion. Okay. And you would see this mostly in the Born-Haber cycle, because you would use this as part of the process to complete the Born-Haber cycle as electron affinity. Same with first ionization energy as well. You would need that for a Born-Haber cycle as well. And so with HL, this table means more to you because you have to use these values to actually calculate. For SL, you're just trying to explain the reason for the values. but not really actually apply the values. Electronegativity. Okay. Has to do with bond polarity. Okay. When you take the difference in electronegativity of two atoms, you can find out whether the bond is polar or not. And it falls into 3 categories. Okay. Non-polar covalent, polar covalent, and then ionic covalent. Okay. Now, the numbers 0.4 and 1.7 are up for interpretation. Some books will say 0.5 and 1.6, some will say 0.4 and 1.6. That doesn't really matter. The IB will generally give you examples where it falls right in the middle of the zone so that there's no doubt. They're not going to give you one that's like 1.6 and ask you whether it's polar or ionic. It'll be like a 1.0, which is right in the middle of polar covalent, so there's no question about your ranges and there's no misunderstanding. So electronegativity is kind of tells you what type of bond polarity you have. And those are your 3 options: non-polar covalent, polar covalent, and ionic covalent. So remember, non-polar covalent means no dipole. Polar covalent means there's a partial positive and negative. Ionic means there's a full kind of positive and negative attraction. Questions? Vice versa. Yeah, it's a lowercase delta. So yeah, if you just write an S that curls upon itself, that's lowercase delta. Okay, the last table is atomic and ionic radii of the elements. Okay, now this is not a calculation periodic table. This is not when you have to use these values to calculate. This is a explanation table. So this is the IB will say, looking at table 9, explain why this ion is larger than this ion or this ion is smaller than this ion using the values. One of the key things that you need to think about in the IB, and I've said this before, is anytime the IB question states a certain table or states a certain thing to refer to in the data booklet, you have to cite that in your answer. So if they ask you to compare the atomic radii between 2 elements using table 11, you need to cite the values of the atomic radii in your answer, because that's the only way you can prove that you actually use that table to answer it. So if they say using table 11, using table 12, using table 13, cite the data from that table to show to the IB that you actually looked at that table, or you won't get full credit. They expect you to list the values here. Okay. So you have normal charges for each of these ions here for the ionic radii. So that will help you a little bit as well with bonding and stuff like that. But again, this is more about just kind of explaining why something is larger than the other. Okay. So like, for example, they might ask, why is sulfur significantly larger than phosphorus? And so again, go back to your orbital diagram. Anytime you talk about atomic trends and stuff like that, orbital diagrams kind of help you explain exceptions. So when you look at sulfur, you see 1s2, 2s2, 2p6, 3s2, 3p3, or 4, sorry. So that's 3s2 and that's 3p4. Phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. Okay. Now, we're comparing ionic radii here, okay? phosphorus is sulfur, okay? What ion did the IB choose to give you about sulfur? What ion?
2 minus?
2 minus, which implies what would we do to this orbital diagram? If it's 2 minus, what's happening?
You take away, you add 2 electrons, so it has a complete outer shell.
Yeah, you add 2 electrons to have a complete outer shell, okay? And so it's actually going to get bigger because you're going to have more repulsion. So S actually gets bigger when it gains electrons and the electrons force each other to repel and spread out. But the phosphorus ion they give you here is 5 plus. And what 5 plus means is you're losing that entire energy level by losing 5 valence electrons. So what you've done now is you've lost a whole energy level, which is why the ionic radii is only 38 and not 184, because you've lost a whole energy level with a lot of protons pulling the rest of it in smaller and smaller and smaller. Yes, Tony? Oh, yeah. Yeah, anytime you have more electrons added to an atom, they repel each other because all electrons are negatively charged. So when you put more electrons in there, just the existence of the additional electrons makes them want to spread out more.
So it's less stable?
It's not less stable. It's just that the repulsion spreads out the atom to be a little bit larger. That's not necessarily stability. Stability is the spin of them within the orbital diagram, and this is more stable because everything is full and they're spinning opposite ways, so everything's balanced. Yeah, yeah. So
why isn't it 3 minus?
well, it usually is, but the idea is giving this to you intentionally for you to be able to explain that difference. So yes, phosphorus is usually 3 minus, but they're giving you this specific example because they want you to be able to explain this. And that only works if this is 5 plus and not 3 minus. Correct. Yes. Because you're adding 2 electrons, but you're not adding any protons. So that naturally allows it to spread out a little more. Yeah. And that's a key thing as well. That's something you also want to say is like sulfur has more protons, so it should be smaller, but sulfur is gaining electrons, spreading out, phosphorus is losing electrons, so the proton to electron ratio is drastically different now. And so the phosphorus will pull it in much more tightly because it lost a whole energy level. Okay. Questions about that? So yeah, this is mostly explanation. Okay, 2 more tables to go. Okay, this one is also another conceptual table for SL and HL. You don't have to calculate anything with bond lengths. It's more about comparing bond lengths and talking about how they compare to each other. This is a cross table. If you're not familiar with cross tables, you have 2 axes, and wherever the 2 axes intersect, that's the value for that. So for example, if you want to find a carbon-to-carbon bond, you'd go carbon here, and the bond length would be 154 pm or picometers. Hydrogen would be 74, and these are all the single bonds. Okay, so know how to read the table first. The multiple bonds are listed down below. Now, carbon-to-carbon single bond is 154, carbon-to-carbon double bond is 134, triple bond is 120. Okay. Benzene is 140. Okay. Why does benzene's bond length of 140 make sense compared to the other carbon-to-carbon bonds lengths here, Marissa? It's about 1/2, correct, because benzene has alternating double bonds that rotate around, so each bond is effectively 1.5 bonds, so it's stronger than a single bond, but it's weaker than a double bond, so the bond length should be right in the middle between those two. Not exactly in the middle, but somewhere in between. Alexandra. Because the stronger the attraction between the 2 atoms, the closer they can get to each other. So the more bonds you add, the more pull the atoms have toward each other, so the shorter the bond length. You're welcome. Now, a couple other things. N2 is triple bond N. You have to remember that. So the bond length of N2 molecule is 110, not 146 as up here, because you need to know some of these common bonds. Oxygen, O2 is 121, not whatever it says up here as 148. So knowing some of these common diatomics and their bonding will help you. Wait, what? No. Yeah, it's an N single bond, Tifa, but you need to remember that N2, when I write that, is a triple bond, and that will affect your understanding of the values. No, not really. For bond length, there's no calculation. It's just knowing kind of comparison of bond lengths here. Like, I guess the one question I've seen the most here is carbonate resonance. It's the one where it's like the double bond fluctuates around 3. So they might ask you to estimate the bond length of that carbon to oxygen bond. So, well, what values would you use as a reference to be able to predict what the bond length of CO3 would be? What would you reference? Yeah, Tifa. 1 and 2, right?
Oh, yeah.
Yeah, 1 and 2, yeah, because it's a double bond that's fluctuating around. So you'd look, okay, CO is 143, C double bond O is 122, so you guess something like 130 or 133. And the IB wouldn't take a look for exact number. They'd say, oh, is the student between these two values? If it is, then that's fine. So estimating these things is something that you have to be able to do, but no actual calculations. Like there's not like an exact number they're looking for here. C single bond O, because with carbonate, the double bond fluctuates between 3 areas. So each bond is like 1 1/3 bonds. So therefore the bond length should be shorter than a single bond, but longer than a double bond because it's not as strong as the 2 bonds. Does that make sense, Marissa?
Yeah, is there not a molecule that's like 2.5?
I think you're just making that up.
It's just one, it's just,
Yeah, it's usually just a double bond.
and that one comes up.
Yeah. Okay. Last table for this section. Okay. This is calculation. So HL and SL alike. Okay. For delta H of the reaction. So this is using bond enthalpies and average bond enthalpies for that. Okay. Now, just to talk about terminology here a little bit. Bond enthalpy is an exact value where there's only one ever possible bond that has that value. So something like Br2 or F2 or Cl2, there's only one time ever that they exist that bond is that way. So that value is exactly that way. Average bond enthalpy is when you have a bond that shows up in a lot of different molecules and they're not all exactly the same. And so instead of trying to dissect each and every single bond, we find an average value that we use for that. And so what we do is, let's say, for example, we have a CH bond. We're trying to find a CH bond here. Well, we could take CH4 and break it up into C and 4 H's, break up all the bonds and see how much energy that takes. Okay. If we knew the value of that, how would we figure out the average bond enthalpy of that? What would we do to that value to figure out the average bond enthalpy? What would we divide it by? How many bonds did we break? 4. So we take this value and we divide it by 4 to get the average. Because we broke 4 bonds, we saw how much energy it took, and then we divided by 4 just to find out the general average of the bond enthalpy. Now, again, cross table for all the single bonds, and all the extra multiple bonds are down here. Again, N2 is a triple bond, O2 is a double bond. That's where students make a lot of their mistakes because they forget and they use the wrong bond enthalpy for N2 or O2, and then their answer is completely off, which is like 2 out of the 3 marks for your whole answer. Bless you. What I try to make y'all do when we do this is to draw all the species and however many of them you have, because a lot of times students see coefficients and they just assume every molecule has one of those bonds when there may be more. So like you may see something like C2H4 plus O2 yields CO2 plus H2O, and you might see something like this. And students just start saying, well, there's C double bond O, so there's 2 of them. There's OH bond, there's 2 of them, but there's not really, there's 4. Because each molecule has 2, so your coefficient is actually twice as many as that. So what I say is you draw it out, okay? C2H4 looks like this. O2 looks like this, 3 of them like this. CO2 looks like this, and water looks like this. Now it's much harder for you to forget to count a bond because it's all laid out for you there. So it's much less likely that you're going to forget a C to C bond or an C to O bond or stuff like that because you drew it all out. So you can now look at the paper and go, okay, I've drawn it all out correctly. So now I can look at these values. There's 1 C to C double bond. There's 4 C to H bonds. There's 3 O to O double bonds. There's 4 C to O double bonds. And there's 4 O to H single bonds, okay? So that way you get all the right bonds. Because again, if you miss 1 bond, you miss 2 out of 3 marks because you get 1 mark for each side of the reaction calculated correctly, and then 1 mark for the overall answer. So if you get one side wrong, you've lost 2 out of 3 marks. You can't get the right answer overall. So again, this is one of those things where, again, your mind plays tricks on you. It's better to draw everything out and look at the paper because your eyes are more reliable than your imagination. Okay? I understand what it's like to be in a stressful situation like that and make mistakes like that. Like, I'm trying to prevent y'all from doing it because it's easy to think about this here when I'm talking to you about it, but on a test when you've got 2 years worth of material crammed inside your head and you're trying to access it at a really, really rapid rate, it's better just write it on paper to avoid that mistake. So you would add up all these values here. And you'd add up this delta H here. And you'd add up this delta H here. Okay. Now, once you've got those 2 values, what's the sign of delta H on the reactant side here? What's the sign of delta H on the reactant side? What are we doing on the reactant side? What are we doing with bonds on the reactant side? You're breaking them, which means what do you have to do with energy, Sammy? You have to put energy in the system. So therefore, the sign of that side is positive. Exactly. On the right side, we are making bonds, and that releases energy. So this side is negative. And then you add the 2 values together, and that equals your delta H of your reaction. Some people will say reactants minus products. That's acceptable as well. But again, don't memorize that because, again, if you memorize it wrong, you have no idea whether you memorized it right or wrong, and you're just flipping a coin to risk points. And that's not the way you want to treat chemistry IB exam. You don't want to leave anything up to a coin flip. You need to make sure that you're confident that you know it's the right way and that it all makes sense. And that's why I stress understanding why these signs are the way they are to avoid those kind of mistakes. Yes, Tene.
Wait, so breaking bonds absorbs energy?
Breaking bonds, yes, absorbs energy. Because the reason why things are bonded together, Tene, is because they share electrons, which lowers their energy state.
Yeah.
But if you want to separate them, you have to give them both enough energy so they can be independent, which means that they have to absorb energy to go apart.
Okay.
I think the analogy I used to do in the past was like, if you're in a relationship with someone and you're like sharing a home or an apartment, it takes less money for each of y'all to be able to like live the life you want to live. But if you break up, each of y'all need more money separately to live apart than you do when you're together. So it takes more, and you have to absorb, you have to get more money. But if you're single and then you get together, then you have excess money. You have money that you can spend like freely. So that's why it's negative. Wait, what do you mean?
Like your rent is, like if you both have some rent and then you live in an apartment.
You share the apartment, right? So each of you are paying less rent, so you have more disposable income. Well, we're not going that far. We're not letting the Bonds have kids. We're just talking about the initial relationship aspect of it, okay? We don't need to talk about little O2s running around, okay? It's just the original bond forming and bond breaking, okay? I can't believe I just like recorded myself saying little O2s running around. Okay. All right. That is the end of part 1. Okay, I will record part 2 tomorrow. Don't forget it's 12 to 3 tomorrow. I don't think it'll be 12 to 3. I think it'll be probably more like 12 to 2. All right, stopping recording now.